Okay, Assalamualaikum warahmatullahi wabarakatuh. We're going to continue with the three-phase full bridge or full wave control rectifier or six-pass rectifier, right? Okay, so let's look at the circuit first. Okay, so this is a three-phase full bridge fully controlled six-pass rectifier. So before this we have a diode as a uncontrolled version. Diodes connected in D1, D3, D5, D2, D4, 6. I always emphasize on the importance of the labeling of each diode or thyristors. Okay, so you must have this all the time. T1, the arrangement should be in the sequence of T1, T3, T5, and then we have T2, T4, T6, right? So okay, so now when it comes to the thyristors, we're going to look at the thyristor also will be connected in such a way we have T1, T3, T5, T2, T4, T6. Okay, before we go into the circuit operation, we need to understand what will be the pulses to each of the diode of the thyristors. Okay, so you need to understand how to trigger all these thyristors and what will be the firing angle and how to do it in practical. Okay, so before that, let's start with the look at the region of operations. Okay, we're going to look at the region of operation for each thyristors. So if I might put in from the previous uncontrolled version of rectifier, we already identified the operation, the region or the range of diode 1 until diode 6, and now we have T1 here because we look into the highest potential of top group, and we look into the lowest potential for the bottom group to identify which diodes will be on at any particular time. So we have T1 and then followed by T3 because okay, come back to the T1. So we have red phase voltage is highest, so T1 will operate, and for T3 you're going to see that the yellow voltage is actually at its highest, and then finally you have T5, the blue voltage at its highest, right? So this is the range of T1, T3, T5, and for the bottom group we're going to have this is T2, and then we have T4, and then come back to the T6, and it will continue to flow front end. So we have T4, T6. So that's why if you arrange in such a way, we're going to have T1, T2, T3, T4, T5, T6. Okay, so we're going to see the sequence of the diode commutation, thyristors of commutation from T1, T2, T3, T5 in the sequence. Okay, all right. So for if we want to look at the firing angle for each thyristors, now we think of the alpha will start at this particular point, isn't it? So that will be the reference for alpha because this is going to be alpha equals to 0. All right. So this will be fired or will be supplied to thyristor 1. You only need to provide the firing angle for thyristor 1, and the rest will be actually only the phase shift version of that firing angle. So here you're going to have alpha plus 120 degree, is that it? Because we have 120 degree duration, and then for this T5 we're going to have alpha plus 240 degree, and for the bottom group you're going to see that this will be alpha, so from there to there is 120 degree, so this is in the middle between 120 degree, so you're going to have only 60 degree from there to there. So here for T2 going to triggers at alpha plus 60 degree, and here followed by the 180 degree, and finally you have alpha plus 300 degree. Okay, so that will be the alpha to thyristor 1, and then that will be the firing angle for thyristor 3, followed by alpha plus 240 degree for T5, and for the bottom group you have alpha plus 60 degree for T2, and then you have 100 and for T4, and finally you have 100 plus 3 pi plus 300 and degree to 6. Okay, so in practical, if you want to have a single thyristors, 6 thyristors, so this is the supply pulse, the pulse to the each of the thyristors, but the control parameter is only the alpha, the firing angle for the thyristor 1. You only need to find what is the value for alpha, and then the rest is only phase shift of that alpha. Okay, so that is very much the control pulse to your thyristors. And now we're going to look at the circuit operation. But before that, if you realize in this note, we start with the highly inductive load, isn't it? But normally we're going to analyze with the purely resistive load first. Okay, this is actually the purpose is actually that will be the analysis for your assignments. So the analysis for the R case will be in your assignment number 1. Okay, so if I can refresh back. So yesterday's we have the first session on the 3-pass rectifier, half control 3-pass rectifier with the resistive load. With the purely resistive load, you're going to have 2 cases, isn't it? The continuous, and you have another one which is case 2, which is from 30 degree pi over 6 until 150 degree 3 pi over 6. Which is 150 degree, which is 5 pi over 6. Right, so for the 6-pass rectifier, so you have a group of 3 members each, then you need to identify theoretically what will be the case 1 for full control 6-pass rectifier. Right, if I may show there, this is your assignment. I'm going to upload that into the Padlet, and please download and do it with the group. Okay, consider a 6-pass full bridge fully controlled rectifier with a purely resistive load. So you need to sketch all necessary waveforms to show continuous and discontinuous conditions, and then you need to identify the range of alpha, because for half bridge half wave rectifier we know that the continuous start from 0 to 30 degree, and from the discontinuous is 30 to 150 degree. But what will be for the range for the full bridge? So you need to identify by sketching the waveform, and then look at point by point and what will be the range of alpha for continuous and discontinuous operations. Okay, and then derive for the average output voltage equation. So this is very much you need to do this is the theory. Okay, so this is theoretical derivation, so you have to base on the theory. So you need to watch waveforms, sketch a waveform, and then you need to derive from that particular waveform. Is it? Right, now assuming V line to line 415 volt RMS, this is RMS line to line voltage. R load is 20. Calculate VDC with the firing angles of alpha 1 and alpha 2. So here what will be alpha 1 and alpha 2 will be different from each group. All right, so you need to refer to the next page. So I already gave it according to the piece group, your group. So that will be the value that you need to use for your group. Okay, so group B and group D. So look at your number of your groups, okay, group numbers, and then look at the alpha 1, alpha 2. So everybody has a different answer, and then you're going to have a different answer from theoretically as well as the EC. So by you need to do it in simulations. So you have to repeat all this by simulation. The first, so in first part you're going to do it in theoretically, which means you need to sketch the waveform, right, and show it the derivation, and then identify the range, so you have to show by PSIM your answer from PSIM and the theoretical calculation are agree with each other, and then derive for the average output. So of course what you do is of course you don't derive from PSIM, isn't it? So finally you do for number 4. So you have to calculate first. This is from your derivation, and then from your PSIM. So you need to compare both results, right? At your PSIM. So that group assignment is a maximum of 3 students per group. You already assigned, you already have your own group, and the deadline will be after the Raya, right? Thursday 28th. So you have a plenty of time to do. So please make sure that do it yourself, everybody involved, and everybody know how to simulate the circuit. Of course, again and again, it's not easy, it's difficult. As a learning process, you need to do it yourself. Okay, try to understand, because this is knowledge. All of this is about knowledge, not about a certificate or degree that you're going to have later on, but more to your knowledge, isn't it? Okay, so this is assignment 1. So therefore I'm just going to show you the simulation. You can use the simulation from the half control that I've given to you. But we need to, so this is a 3-phase full bridge. So now you need to change that to from the PSIM circuit that I gave it to you from the Padlet. The Padlet shows the half wave, so you need to use, now you need to use the 3-phase. Look at that, 3-phase thyristor bridge. Okay, so you click here, and then the bottom here it shows that 3-phase thyristor bridge, and then the rest is similar, right? So R and B, because you want to detect. If I can quickly show you the waveform. So you have to remember, always try to sketch the waveform. The more you practice, the more you will expert in drawing the 3-phase voltage. Okay, so quickly I'm going to draw the phase voltage for the red yellow phase voltage. Okay, so that will be red, yellow, and blue. I'm going to extend that to the tip. Have that. So that then red, okay, then you have the yellow, and finally you have this blue. Okay, so again, this point is very, very important, isn't it? So we have V red here, and this is V blue. Okay, so if you measure, this will be 30 degrees from there to there, right? It's 30 degrees. This is known as a commutation angle. This determine where is alpha equals to 0. This is determine the alpha equals to 0. So in practical, in simulation, you need to sense. You need to sense the VR and VB, and then there is a comparator here. Whenever VR equals to VB, then it will trigger VR equals to VB. Then it will trigger the comparator here again, right? This is actually the sensor. This is sensor. This is comparator. And once it when it detects VR equals to VB, then it will instruct or it will tell the alpha controller here where is this alpha equals to 0. Okay, so that will be the point. All right. Okay, and what else? Okay, in another thing is, when you do the simulation, make sure that the pulse is the white pulse. Remember, before this I mentioned that for the thyristor, it is enough for you to supply a short pulse, isn't it? A short pulse. Okay, but for this 3-phase full bridge rectifier, when you want to simulate this case, you must have a long pulse, which means it will start from there to there, 180 degrees. For example, this is your alpha. It will stop at 180 degree. So whatever alpha that you choose, the end will be 180 degree. So that's why here you have this alpha controller here with the 180 degree. Previously, for the half wave rectifier, if I'm not mistaken, you have this 2 degree, 2 degree, but now it has 180 degree. Okay, and then you analyze and change the value, and as well as you look at the waveform. Just again for the hint, for theoretical waveform, you need to master how to sketch the three-phase line-to-line voltage. Okay, in the monograph I did show you how to sketch the line-to-line voltage. It's a bit different with the phase voltage. Sketch the phase voltage. Okay, for the line-to-line voltage, what you need to do is first you draw the triangle. Make sure that you have at least 3 triangle. Okay, next is to sketch the reciprocal of it, the mirror image of the first triangle. Okay, if you use a ruler, then it will be accurate, more accurate, and this is just a sketch. Okay, all right. Next, to have another triangle in between. So you start from here, just run through on the in between. Again, practice makes perfect, so you have to practice this again for your knowledge, isn't it? Okay, and the mirror image of that, no problem, just the mirror image of that. And there you are. Great. And finally, you connect the tip of each triangle there. So you have that. This will be your line-to-line voltage. Okay, and the bottom group. If you do 4 triangles, okay. So if you do it 4 triangles, then you have 0 level at that particular point. This will be your 0 voltage. This x-axis here will be 0 voltage, and this will be your V line to line. Okay, so if I can do that, you just simply bold it, right? Make it bold. Then you have a nice 6 line to line voltage. Okay. And finally, you have another one here. Don't take it for granted. Don't leave it until the end. Then you want to sketch. So why not you practice from now? Just take a plain paper and your pencil or your pen, then start to sketch. Practice again and again. Then you can get a nice line-to-line voltage. So here we know that this is 60 degrees, isn't it? Okay, this will be your 60 degree, and then when you start to trigger your thyristors here, then you're going to see there will be a your waveform will start to move a bit, isn't it? So this is will be your alpha. Okay, then your waveform will do that. It will follow this line-to-line voltage. Okay, so identify when it start to hit this, when you're going to see. So you need to increase alpha from 0, then start probably 30 degree and 60 degree. Okay, just move a bit until you reach alpha, the angle close to, you have the point of 0 levels there. Okay, so that will determine the continuous and discontinuous operation. This is a hint, right? I leave it the rest for your assignment. Okay, and again, it will due until after Raya, inshallah. Okay, right. So now we so you know that you're going to have a first assignment, which is on the resistor. Now we're going to look at the case of highly inductive load, R plus L, right? So we just consider we have a highly inductive load. Therefore, you're going to remove R plus L, and then you're going to put in the a constant current at the output. Okay, so this is the rearrangement. We're going to manipulate a bit just to show you that we have this is very similar to the midpoint converter, the half wave converter, right? For the top group, P group, and then we have an N group. I think this is very much similar to the uncontrolled version, right? So here, this is your waveforms, right? So here we have this alpha. Okay, if I can, so alpha with a certain value, and therefore the output voltage will follow the alpha here, Z. So this is okay. Previously, without the source without the or alpha equals to 0, you're going to have nice 6 pulse rectifier, Z. Alpha equals to 0. This is very much similar to operation of the diode operation. So you're going to have a nice 6 pulse rectifier. Okay, then when you start to have the alpha, the firing angle, therefore you're going to see that the this is actually the T5. Thyristor 5 is operating, so it will continue to operate until you trigger thyristor 1. Okay, so thyristor 5 will start to will continue to operate, yeah, until you trigger thyristor 1 at this particular point, is it? All right, so that's why you have this output voltage now. So output voltage with like a sawtooth, just like a sawtooth. So that will be the. And when we talk about the current, okay, if you talk about the current, then we have this. This is the current for blue phase. It will continue to flow through the blue phase, the T5. This is T5, and then you start to trigger thyristor 1, is that it? Then you have thyristor 1 trigger the point. So now you have a raise of current will start to raise from 0 to T1 to IDC. This is IDC, and then blue will instantaneously falls to 0 from that point. Okay, so that will be your waveform for the current, right? Okay, so focus on computation T5 to T1. T5 keeps on conducting until omega T equals to alpha, and then current commute instantaneous to T1. So this is to describe the current commutation from blue phase to red phase, T5 to T1. Okay, so now we're going to look at the analysis on the voltages of current waveform. Again, we just consider one pulse. Take only one pulse. Okay, so we're going to consider this pulse only. And as what we did for the previous analysis, we're going to shift so that the peak of the pulse here is at its 0 angle or 0 degree. 0 angles here. So therefore, this will become V line to line peak. Cos. It should be cos. Cos theta, isn't it? Right? So because we have a pi over 3, so now you have minus pi over 6, which is 30 degree, minus 30 degree there, and then you have a plus 30 degree there, and therefore you consider the firing angles, then you have minus pi over 6 from that point, the firing angles, until you have this pi over 6 plus pi, the alpha at that point. So you need to integrate from there to there, and therefore you have this integration. and you have to divide by 60 degree, because one pulse equals to 60 degree. So to get the average, we have to divide by 60 degree, and then we integrate this, and I've already given to you the how to integrate that. And again, make sure that you understand how to evaluate this. And finally, you find out that the output voltage VDC equals to 3V peak line to line over pi cos alpha. Okay, so this is the angle, the equation for the highly inductive load conditions, right? Highly inductive load conditions. So remember, for R, you're going to have, if you consider the purely resistive load case in your assignment, you're going to have two different output voltage equation for continuous and VDC for discontinuous. So you need to find out what will be derive, what will be the equation for both conditions here, in the assignment. Right? Okay. Next. Okay. So don't remember, you also need to find the RMS. So probably in the assignment, okay, remember assignment, I'm going to add another question. So you need to add in your assignments to find what will be the VRMS and show from theory as well as the PCM. So you need to compare the results, the RMS voltage for by theory and also the PCM. So you need to derive and show me in this assignment what will be. So I've already give you the hint. So you need to start from there and then evaluate and get this theory and compare with the PCMs. Why? Because I always consider that I always emphasis on you, because we have this question, the final exam question, that asks you to find the ripple factor. Okay, the ripple factor, whereby you need to find VAC, and you can also only find VAC if you know what is the VRMS of the output, isn't it? Okay, so there is a one question last semester, if not last two semester or last semester, that asks you the RF ripple factor. So in the assignments, I want to add another, whether even though I'm going to add that later on. You're going to also prove what will be the RMS of the output voltage. Okay, so now we're going to look into the analysis on AC side current. So I think from the previous the uncontrolled rectifier, we know that we are already given the Fourier series, isn't it? The Fourier series, we have already analyzed the Fourier series of the we called it as a quasi-square waveform, isn't it? This is a quasi-square waveform. Okay, and for quasi-square waveform, we know that Cn equals to 4IDC over n pi cos n pi over 6, if I'm not mistaken. So check back with your previous note. And then however, n only exists for one, which is odd, but there is no triplen, isn't it? There's no triplen harmonics. Okay, so you could have 1, there's no 3, next 5, 7, then no 9, then you have 11, 13, 15, there's no 15, then we have 17 and the rest. Okay, so this is for the control rectifier, the magnitude is still the same, 4IDC over n pi over 6. As what we discussed in the single phase control rectifier, however, the displacement factor, so because we have this phi n, and that also equals to angle of phi, so therefore you have a displacement factor, everything is just a matter of cos alpha, isn't it? Right, so this is very much similar to the control rectifier or single phase full wave rectifier. So refer back to that particular note, and then you can find what will be the THD as well as the power factor, when we have the control rectifier here, right? Okay, so that shows you we have at the fundamental 5th, 7th, 11th, 13th, no 19th, we have this sorry, no 15, then we have 17, and the rest, isn't it? So 1st, 5th, 7th, 11th, 13, 15, 17, 19, and the rest. Yeah? And the amplitude here will be 4 IDC over pi, because n equals to 1, cos n pi over 6 pi over 6. Okay, and you can find that for IDC over 5 pi cos 5 pi over 6, isn't it? So you can find all these values in that Fourier series. And again, for RMS, you don't have to worry. RMS is similar to the uncontrolled version, and you get the square root 2 over 3 I naught. Isn't it? Yeah, similar RMS equation. Okay, next we're going to continue with this effect of load and source inductances. So this is again and again in practical, you have the source inductance. It may come from the cable as well as the transformer at the front side, isn't it? So we always have this. If you can look, this is your inductance, source inductance or line inductance. Okay, so we have this, and just look at the waveforms. What happened is we're going to focus on the transfer of current from T5 to T1, from T5 to T1. Okay, so we're going to focus on that particular transfer of current, commutation of current from T1 to T5. Okay, so this is your, when you start to trigger your alpha, right? So you start to trigger alpha, then you want to so we're going to see that the current in blue phase, which is IT5, reduced with a certain rate, is the rate. Okay, it falls with a certain rate, as well as for the thyristor 1, it rise or it raise with a certain rate. So there is an overlap of current through thyristor 1 and thyristor 5. So both thyristors are on, as well as if you look at this current, we also have this current from the T6, isn't it? So there are 3 thyristors are on when we have this overlapping phenomena happens here. Okay, so 1, we're going to have T1 is on, T5 is on, and for the bottom group, we're going to see that T6, which is connected to the yellow phase, also also on. And so we have 3 thyristors are on during this period, right? So we're going to analyze and to find, and if you look further, you're going to see that your output voltage is actually in the middle between the two line to line voltage. So if we might extend that, this is line to line voltage, and that also another line to line voltage. So this is in the middle between the two line to line voltage. So we're going to find what will be the instantaneous equation for the output voltage during the overlap phenomena, and then we're going to find what is the angle for the overlap interval angle, as well as also we know call it as a overlap angle U. Okay, so here look at this alpha. So this is the start of the firing angle thyristor 1, and then you have this U. U is actually the overlap angle. Then there you have alpha plus U, isn't it? Okay, and then we have this equivalent circuit during overlap. So now during overlapping, So you're going to have IR, which is IT1, and then you have IT5, as well as we have this current. Actually, it doesn't show here. We have IT6, which is also equals to IDC. If you refer back to this waveform, if T6, okay, so T6 operates, on, it will equals to the IDC. So this is IDC here, isn't it? That is IDC. So T5 equals to IDC. All right. Okay. So that will be the equivalent circuit: VR, VB, V yellow. And then we have IR, IB, and then this is I, red, yellow. Okay. And this is your highly inductive load. So we already replaced this with a constant current, I DC. There's no more R plus L because we already changed it to IDC. Okay, so consider that equivalent circuit, and then what you take a KVL around the loops. So around these loops, I'm going to show you. So you're going to take around this loop, through there, through that loop, then come back to that. Okay, so we have if I can write it, minus VR plus LS DIR over dt plus V out, and then we have plus LS DIDC, isn't it? DIDC over dt, then we have plus Vy equals to 0. Okay? So therefore you have V out equals to VR minus Vy minus LS DIR over dt minus LS. And the other loop, the other equation that we need to consider is from that VB through LS, IB, and then you come back to that, come back to that loop. So you have V out equals to VB minus Vy minus LS DIB over dt minus LS DIDC over dt, right? And therefore you add both equations, right? And we know that from the sum rule of differentiations, okay, so this term goes to 0, everything goes to 0, and therefore V out equals to VRY plus VBY over 2. So the average between the two line to line equation. So that confirms the waveform that we see just now. It is in between the two waveform here. So it is the average between the two line to line voltage, and that gives you V out equals to VRY plus VBY over 2. And then next is we're going to look into the overlap angles. So the commutation current IU flows through both diodes due to short pass, and we consider the this loop only, and then you need to assign a current IU which follow the current that flows after overlapping period. So we know this is transfer of current from T5 to T1. So you must assign a current that follow T1. Okay? So in this example, in this circuit, this is your IR or IT1 or IR. Okay, and this will be IT5 or IB, right? So you need to follow this current. So you assign IU current that follow IR. Okay, and that is to ease you to do the analysis. Then we have this KVL around the loop. Then you have these 2 omega LS IDC. You solve that, and finally you find out. So remember, you have alpha plus U, and then you have 0 to IDC. And look into the current, IR current, red current waveform. If I can go quickly go back to, so you need to refer to this current. So it is an integration from 0 to IDC, and for the voltage is from alpha to alpha plus U, right? So you do that, finally you find out that your angle, the overlap angle is equals to inverse cos alpha minus 2 omega sine dc over v peak line to line minus alpha. So always treat this in radian. Okay, put everything in radian. Treat everything in radian. Don't mix up. Sometimes you put this 100, you know, you put in degree. No, you cannot do that. Do not mix between degree and then radian. Okay, so always treat them as in the radian. Okay, and finally you need to find the average output voltage, isn't it? So similar approach, we know that we already know what will be the waveforms for the control rectifier without the source inductance. Okay, we already know that from the previous analysis. We already find what will be the output voltage equation without the source inductance here. Okay, and now we just simply find the voltage drop here, isn't it? Once you know what is the voltage drop here, then you can find the average of the output voltage with the source inductance. With the source inductance. Okay, so we need to find what is this small area here. So it just simply you integrate. Okay, you integrate from there to there. That's it. Right? So you still have the same alpha plus u, and then therefore you have the area equals to VRY minus VBY divided by 2. You also can do this integration, which you integrate the whole area here, okay, and then you minus with this area VBY, remember, so that gives you this area, isn't it? Okay, but we know that this wave the voltage actually run in the middle between the two, so you can divide by 2, right? So when you divide by 2, then you only focus on that area. Okay, so that is what the equation does. So VRY minus VBY over 2, and that gives you VRB2 theta. And if you compare with the equation before, you will find out that the voltage actually equals to V line to line sine theta. Just compare to one equation this, VRB equals to V line to line sine theta theta, and this gives you result 2 omega SI DC. Okay, so if you manipulate a bit, then you can find that this area voltage drop equals to omega LS IDC, and then the average voltage drop you just divide by 60 degree, then that gives you 3 omega LS IDC. And finally, the average voltage becomes 3 V peak line to line over pi cos alpha minus 3 omega LS IDC over pi. Okay, so again, the source inductance has caused reduction in the average output voltage because you have a negative area here. Okay, so there's a reduction in the average output voltage, as well as the distortion, and this distortion is specifically known as a notching, the voltage notching to the point of common coupling before the rectifier. So normally when you in your system, you're going to connect that point not only to the rectifier, so that will be your first load. Okay, you might as well want to connect that to another load here, so that will be load 2. Okay, so you can connect that to load 2. Right, therefore if you look at the waveforms now, this point, the voltage is no longer sinusoidal as supplied by the TMB, because you have this rectifier, and that rectifier has produced, because of source inductance, there is a missing area, and that missing area reflect back to the front end, that causes this notching at the front end. Okay, so therefore your load 2 will see this distorted voltage waveform. So this is load 2. So there will be a harmonics related problems if you have this supply is not sinusoidal. Okay, I think that's all for the rectifier, control rectifier. Next we're going to I think, please, again and again, please do download from the internet and do all this exercise, and always ask me questions. I welcome all questions from you. Okay, so but you need to try to do it first, and then we're going to discuss. Okay, thank you very much.